Hello, everyone. Very excited to be here and to welcome you to our tutorial and workshop on efficiently fine-tuning and serving open source large language models. I'm Alex, and I would like to propose that we first review some key concepts and then dive into actual code, into a walkthrough, and it'll show you how to easily build your own set of fine-tuned models that rival GPT-4. I will first offer an introduction to our recent LoRaWAN launch and an overview of adapters and why they're the future of fine-tuning. That will set the context for us to go into the engineering aspects of LLM fine-tuning, the open source frameworks, the Predibase service, and then an actual code walkthrough for fine-tuning 3 adapters for a practical application scenario with Predibase. That will be our illustration. Awesome. So let's talk about LoRaWAN and some of the underlying motivations. LoRaWAN is our playground. It shows how we fine-tuned 25 models that rival GPT-4. By rival, we mean that they are at an equal or better performance. And today, I couldn't be more excited to show you how you can build your own version of LoRaWAN. We will use the customer support domain for the illustration. Before we dive into LoRaWAN and why we built it, I think that it would be helpful to take a step back and see how most teams have started experimenting with large language models. We see that most teams start with a commercial LLM like OpenAI or Anthropic, and the appeal is pretty clear. Users now have access to a large language model with trillions of parameters. These are essentially complex reasoning engines at their fingertips with just an API call away. However, we start to see very quickly that many teams run into hurdles with these commercial LLMs. Number one, cost. Some companies are spending upwards of millions of dollars on OpenAI once they have it in production. Then there is latency, because these models are so large, you're stuck with whatever speeds the providers give you. And these models are not yours. If you believe that your data and your models are your intellectual property, then it's clear that having ownership over your models is the key to building a defensible generative AI strategy. So if OpenAI isn't the future, then what is, right? Why not just keep using OpenAI for everything? Proof of concept, prototyping, development, production? Well, the truth of the matter is that actually relying on OpenAI as part of a real commercial grade application in production environment is problematic. We believe that while it's common to start with OpenAI, you can gain some experience with LLMs, but using smaller, fine-tuned open source models when you're ready to move to production often provides better trade-offs. When we talk to organizations today, we find that while using a large model like GPT-4 is fine, what developers are really trying to do is solve specific tasks, like build a question and answer type chatbot, build a text classifier or summarizer, generate structured output like JSON, things of that nature. In addition, by using open source models, you can immediately see several key benefits, including the ability to own your models, stop sending your data to these external commercial LLM services, and make use of smaller and faster LLMs, which you can fully control. So our recommended approach is LLM fine-tuning. Here is how fine-tuning works at a very high level. Large language models are good generalists, but they have little specialization. They're trained on many different tasks, so they know a bit about everything, kind of like jacks of all trades, but not enough about anything specific. Nevertheless, it turns out that there are ways in which we can also train them to solve a particular task very well, that particular task and nothing else. We call this customization process fine-tuning. We start with everything the model knows and adjust its knowledge to help it improve on the one particular task we care about. Essentially, the premise of fine-tuning is that base models are pre-trained on gigantic data sets, which makes them very general and not able to perform well on specialized tasks. But fine-tuning does accomplish this. In addition, a big advantage of the fine-tuning approach is that the custom domain-specific data sets do not need to be large. Typically, small, high-quality data sets with 5,000 to 20,000 samples are sufficient to get a good, fine-tuned model performance. Now, in the world of fine-tuning LLMs, there are broadly two approaches: full fine-tuning and parameter-efficient fine-tuning, or PEFT for short. In full fine-tuning for large language models, you have your data set and you're aiming to update all of the model parameters during each step of training as you pass over your data set. This is very expensive from both a memory perspective as well as a runtime perspective, because you have to track the activations and gradients for all of those parameters in your model when you update the weights during training. However, in recent years, PEFT became an alternative that's gotten popular. Instead of adjusting all the weights of the model, we introduced a small set of new trainable weights and only update these weights during training without touching the original base model weights. And so the result is that we keep the base model the same, and the new set of weights, which we call an adapter, is very small, usually on the order of about 1% or so of the total model parameters. But it tends to match or exceed performance on a very large variety of tasks. It might seem counterintuitive that just training a very small percentage of weights can do so well. There are a couple of general reasons for why this works. For one thing, most of the knowledge is already learned by the base model, so we only need to tweak a few weights to teach it our task. Another reason is at a more fundamental level, and that is because we freeze the original pre-trained weights, we also avoid a very common problem with full fine-tuning. It's called catastrophic forgetting, where the model forgets previous information such as grammar and language semantics while learning new information about our particular task. Over the last year, one such adapter fine-tuning method that has gotten a lot of popularity because it works so well is depicted on this slide. It is called low-rank adaptation, or LoRA for short. In this technique, we basically introduce two new tensors, A and B, alongside linear layers in the original model. This happens in each transformer layer in your model architecture. During the forward pass, the input from the previous layers is passed through both the pre-trained weights and the LoRA layers, and then summed together before passing it to the next layer in the model. During backpropagation, the pre-trained weights of the base model are completely frozen and untouched, and we only update the LoRA adapter weights using the loss information. Now, to see a real example, here we have a common use case of JSON generation. We ran benchmarks comparing a fine-tuned 7 billion parameter model against GPT-4 and found that not only was the fine-tuning actually more accurate, but it was also 250 times smaller as a model. Why does it matter? Well, if you look at Predibase versus OpenAI, there is about 100 times price difference between us and GPT-4. So with open source LLMs, you're truly getting the best of both worlds, better performance at a fraction of the cost. And this is true in most cases, not only for JSON generation. Fine-tuning a much smaller general open source LLM on a domain-specific data set outperforms the proprietary commercial models on these given tasks. And by the way, please allow me to clarify what we mean by smaller. It may be a subtle nuance. When we say that fine-tuned models are small, we are referring to the fact that we apply special techniques, not only PEFT, but also quantization of the numeric representation of model weights. It's data compression. A lot of recent breakthroughs in machine learning engineering have led to the reduction of memory footprint of the model's weight tensors. What it means concretely is that the open source 7 billion parameter, 13 billion parameter, and even 70 billion parameter models are significantly smaller than GPT 3.5 and GPT 4. As a result, the fine-tuning process incurs a dramatically lower cost to customize the open source model. The performance efficacy is comparable or exceeding that of OpenAI and other commercial models. And this is extremely important. Generating predictions from the fine-tuned model comes at a fraction of the cost because inference prediction is the predominant cost factor in production. So let's review the benefits of fine-tuning. One benefit is that thanks to the various optimization techniques, fine-tuning can provide the state-of-the-art accuracy very cost-effectively. And the other benefit is lower inference latency. Smaller models execute faster because with fewer parameters, the number of multiplications and additions needed to compute the output is also correspondingly lower. And so I present to you LoRa Land, our playground of fine-tuned Mistral 7B adapters. LoRa Land explores applications to various use cases, such as mathematical tasks, headline generation, news summarization, named entity recognition, and others. LoRa Land is a very effective showcase demonstrating why LoRa type of fine-tuning is popular. It has been shown that it's just as good as full fine-tuning for a wide variety of traditional benchmark tasks, such as the glue benchmarks. At Predibase, we have also seen this almost consistently over the 1,000 models we have fine-tuned internally. Across multiple data sets, LoRa is extremely competitive and either almost matches or outperforms full fine-tuning. To emphasize what this means, the number of trainable parameters is less than 1% of the total model size on average to get those performance numbers. And beyond lower memory footprint, the jobs are also much faster and cheaper to train. On average, compared to full fine-tuning, it's 15 times to 25 times cheaper and typically 10 times to 12 times faster to train. And so if there was ever a question of does fine-tuning work, I think LoRa Land shows that the answer is a resounding yes. We saw on X, formerly Twitter, that even Jan LeCun, chief scientist at Meta, quote, tweeted our launch and has conviction that the future will indeed be one with many small fine-tuned models. There are many more fine-tuned adapters and examples on the interactive Predibase LoRa land page that you all are welcome to try for yourselves. And our team published a technical report on arXiv. It has been featured on Hugging Face and covered by industry trade magazines. It includes the results of our comprehensive study of fine-tuned models versus GPT-4. We're now going to dive in a little bit deeper into how these systems operate. When we talk about bringing an open source large language model, LLM-based application into production, there are two major components involved. One is responsible for fine-tuning the base model on a high-quality domain-specific data set, and the other is responsible for serving the result. That's the base model with a fine-tuned adapter. In fine-tuning, what is fundamentally happening is that we have a mathematical formula that is a function of billions of parameters, and we are solving an optimization problem. We compute the optimal values of all of these parameters. And optimal here means in the sense of giving us the most accurate predictions when we use this model in our application. As part of the implementation, we are faced with multiple engineering challenges. Finite precision machine representation of floating point numbers. If you get an overflow or an underflow, the result is invalid and you have to start again. In addition, because we use accelerators to speed up the common mathematical operations, there we're dealing with large tensors, multidimensional arrays of numbers that have to fit in the accelerator memory. Graphical processing units, the GPUs, are now most commonly used as accelerators for machine learning. They have finite memory. So if an out-of-memory exception occurs, you have to start over again. There are many of these kinds of considerations that machine learning engineers have to tackle. And traditionally, this first part, training and fine-tuning, has received most of the emphasis from the point of view of mathematics and engineering. However, the problem of model serving is actually even more critical because model serving inference is what is incorporated in the applications. In fact, model serving is the mode that impacts the operational budget the most, because while fine-tuning or retraining happens when the new data is available and you do want to improve your model, inference is happening when the application is used by customers. And that is orders of magnitude more frequent than training, because inference is how we incorporate machine learning into practical applications to serve product recommendations, to automatically respond to common customer support questions, to generate a code in a co-piloting tool, and so on. The inference regime is what is powering our applications. And that happens a lot more frequently than training, a lot more frequent cadence. And it naturally also uses GPU resources. So these are the two primary system blocks, fine-tuning and serving, plus, of course, having access to high-quality data for fine-tuning. We at Predibase maintain two open-source Python frameworks. Two frameworks, one for fine-tuning LLMs, it's called Ludwig, and the other for efficiently serving fine-tuned LLMs, it's called Lorax. Ludwig is a low-code framework. It has now been around for several years. You give it the configuration with inputs and outputs, the base model, and it figures out the hyperparameters by itself in order to train your model in a reasonable amount of time using the available GPU resources with the objective of maximizing the accuracy of predictions that you're going to serve when you deploy your model in your application. Ludwig is very popular because it makes the life of data scientists and machine learning practitioners a lot easier. Now that we have fine-tuned our model, the next concern is serving. So let's say that we fine-tuned a base model for a customer support use case. Let's say to extract the intent from the call transcript. Basically, why did the customer contact support? We fine-tuned it. We have our adapter. We then approach DevOps and request a G5 2x large EC2 instance to host the model. It has a 20 gigabyte GPU. Great. Well, that costs about $900 a month. Fine. Let's say then we also use the same base model to fine-tune another adapter, also for customer support, but this one performs a different function. It gets sentiment analysis of caller-agent conversations. So what do we do now? Do we spin up another dedicated deployment? No, this approach is not cost-effective, especially because doing this will make every GPU extremely underutilized. So LoRaX addresses this problem. LoRaX stands for Low Rank Adaptation Exchange. LoRaX packs over 100 fine-tuned adapters for a given base model and accommodates them all on a single GPU. As the call for a given fine-tuned adapter comes in, LoRaX routes the request to the appropriate adapter and swaps in new adapters as needed based on the use case, while swapping out the adapters that are idle. This is analogous to how virtual memory works in an operating system. The cost savings are over 100-fold compared to dedicated deployments. And fine-tuned adapters, as we showed in LoRaLand, often exceed GPT-4 in prediction accuracy. LoRaX, as an open source library, has a vibrant community of users and contributors. Now, infra for machine learning is hard. There's a lot to consider: abstractions, interface, making things easy to use, enforcing best practices, controls, the efficient training, breaking up the models, the GPUs, using deep speed for training, various tooling. The models can get so big that the infrastructure has to be efficient. It has to, like, you want good utilization out of these expensive GPUs so you don't waste money. You need to figure out the resource needs, right sizing, fault tolerance, failure is norm. You've hit out of memory exceptions. Well, how do you gracefully restart? How do we make this whole cost effective? Spin up and down, monitoring, service level agreements, scale for production and robustness. These different infrastructure layers is what Predibase develops and operates as a hosted LLM fine-tuning and serving platform. Predibase draws from Ludwig and runs on LoRaX inside. So Predibase hides the complexity of provisioning compute resources, including the GPUs, and provides always-on base models and easy-to-use SDK for developers. So we will do our coding work today in Predibase. In our code walkthrough, we will fine-tune 3 adapters for different customer support scenarios and compare their predictions to those of the base model. We chose Mistral 7 billion parameter model as our reference base model because it has exhibited very good performance on multiple benchmarks, and we found it to be easy to fine-tune on a wide variety of domain-specific data sets. Importantly, we must make sure that both the base model and the fine-tuned adapters are compared fairly. We do that by using the same inputs. Otherwise, one may not know if fine-tuning was even necessary. What if the base model is already good enough? So then we can save the infrastructure costs if fine-tuning is not necessary. So it's important to keep in mind. And we will use customer support as our illustration. So we will be like a service provider of auto responses for customer support domain, but 3 different customers. One focuses on payments, the other focuses on orders, and the third focuses on accounts. While they're all in the customer support domain, they're different because the domain expertise for payments is different from domain expertise needed to handle orders and different from the account inquiries. So these will be our 3 customers, and we're a service provider. And our goal is to generate one auto response that is as likely as possible to handle the user's inquiry so that they do not escalate into voice. So accuracy here is very important because it controls costs. If the auto response is ineffective, the user will escalate to voice, which is more expensive. So we want to ensure the accuracy of our one-shot auto responses. And what we will want to do is not only send an auto response, but we will also want to look at the initial inquiry from the customer and learn the intent. Why do they contact support? And finally, we would like to package the output into a JSON structure so that it could be processed downstream. For example, store in a JSON column of a Postgres database, which can then feed reporting, dashboarding, so that the analysts can look at the results and help improve the contact center operations. So we will return JSON, the intent, and auto response. And now the way we will proceed in the code is first, as mentioned before, we will test to see if the base model is good enough. We'll prompt the base model. We will attempt to, we'll do all we can to make the base model succeed. We'll find that it's still not good enough. Accuracy is not good enough. So then we will prepare the data set. And I will go through data set preparation quickly because you will have the notebooks. It's just data manipulation, data exploration, and creating 3 data sets, 1 for each customer. And then we will fine-tune. We'll fine-tune the model for payments, orders, and accounts, and then review. We will prompt the fine-tuned adapters and review their response and see if the quality got better. So I will now stop sharing this particular presentation and share the code that I have prepared here for review. So we begin, and these notebooks, this and some other notebooks will be available for you. We start by importing the Predibase SDK and the dataset library because we will be accessing a dataset from Hugging Face, and so some other needed imports. Then we get the token from the Predibase user interface and instantiate the handle into the Predibase SDK by providing the token to the Predibase constructor. And then we grab a hold of Mistral 7B base model and get the client. That's the reference to the base model. Via this API call, we get the client. Now let's specify a couple of options. Max new tokens, it's a guess, 256. Temperature controls the randomness of the response. And a simple prompt, I can no longer afford this order, cancel it. Let's prompt the base model and see what it will generate. Kind of in the ballpark of orders, but not very good at all. Lots of repetition, lots of unnecessary information. Well, let's not give up. Let's try something else. Let's give it a better prompt and specify the intents that can be obtained for the orders. So orders and payments accounts, they all have their own intents. That's how these customers are different. So let's create a formal prompt, specify the possible intents, and tell it to return the result in the JSON format. So let's run it. Better, but still there is repetition. It's not clear, not crisp, and it's not so good. And there's an abrupt ending, so it's not really good JSON. You can't pass it down to code downstream. Let's try one more thing. Let's provide an example of what we want the output to look like within the prompt, so-called one-shot example. One-shot prompt. So here are the intents, and here's an example: place order, response, thank you for interest, and the rest of the response is there. Let's see how this does. Let's prompt the base model with this. Better, but still a lot left to be desired. So we make a decision that the base model is not good enough. We will go ahead and proceed to fine-tuning. So we'll grab the data set, and the data set is called Bytext Customer Support LLM Chatbot Training Data Set. It has a category column which we can use depending on the values of this category column. We can subdivide this data set into 3 disjoint data sets. One is categories pertinent to orders, the other will be to payments, and the third will be to accounts. And that's how we create our 3 customer-specific data sets, and also obtain the different intents, the sets of intents that are pertinent to payments, orders, and accounts, respectively. So that's our data set preparation, cleaning, eliminating some bad data in the process. Very important. We're just going to skip through it and get to fine-tuning. So here we have our data set. We have the instruction and completion in the JSON format, the intent and the response. We're not done yet. Now that we're going to do some statistics so we know what the maximum output tokens to expect. We don't want the results to be chopped up, but we also don't want to allocate too many tokens because that increases the costs. So with some statistics, we know what to expect, different distributions depending on our training data. So finally, we get to fine-tuning, and we will start with the prompt that has a standard structure for the 3 customers, but the intents will be different. One set of intents for orders, the other for payments, and the third one for accounts, and the instruction will be one from each training sample. And so we will now create the payments data set. These are the intents filled in here, and we will now encapsulate our instruction there, save this, and upload the prompt completion data set to Predibase. So we do it by this API call. We upload from the file to Predibase, give it a name, and now create the adapters repository because we can run multiple versions. And here we launch fine-tuning by creating the adapter. So this command specifies the base model, the number of epochs for training, learning rate, other parameters, the data set, and the description of our fine-tuning experiment. So that ran, and that produced the adapter for the payments customer. We will now do the same for the orders customer. So here's our orders data set. We have the prompt with intents specific to the orders customer. We create this data set now with prompt and completion columns, upload it to Predibase, and launch the adapter now for customer support data set of orders. So this adapter will get fine-tuned and stored. And finally, we do this for the accounts customer. Again, different intents for the accounts customer. So this is delete account, create account, switch account, all of these account-related concerns. We create our prompt and completion data set, upload it to Predibase, and run the fine-tuning by creating the adapter. So this completes. Now it's time for us to evaluate the results. How did it work? Well, that's done through Lorax underneath. By looking at the statistics, we decided to increase max new tokens so that we accommodate the longest of the auto responses so that nothing is chopped off, and keep the same temperature. Now, these adapters, by the way, they're stored on Predibase, but also on Hugging Face. There's that flexibility. So now let's prompt the payments adapter. So these are the payments intents. We have our particular request. Can you help me check in which cases can I ask for refunds? And now let's look at this output. Crisp intent, check refund policy, and an effective response. I'll take care of it, and on and on. High chance that the user will receive this auto response, be satisfied, and not escalate to voice. So let's do this now for orders. So the orders intents. I can no longer afford this order, the same prompt from before, cancel it. Correct intent, cancel order, and the response. I've understood you're facing financial difficulties. I'll cancel your order. And finally, the accounts. Here are the accounts intents. Where can I get information about opening an account? Create account is the correct intent. The response is I'm on it, and the rest of it, and it's in a proper JSON format. So our takeaway is that the fine-tuning was, even in our walkthrough tutorial, in our purported example, has been very effective. So now I will go back to the slides and summarize our results and takeaways. We're leaving some resources for you. So all of the LoRa Land showcase adapters are on Hugging Face. They're under the Predibase repo. You can see them all there. They're available for you to experiment yourself. You can try them live on LoRa Land on the Predibase website. And this notebook that we just went through, plus a few other notebooks, are available for you to experiment with on your own. And to help you along with that, Predibase gives $25 in free credits when you sign up, so you can actually use this API that we just showed and fine-tune your own adapters, prompt already fine-tuned adapters, see the results for yourself, experiment for your own application, for your own use cases. And we would love for you to let us know how it goes. Come join our Discord. There's a group for Predibase, there's a group for Ludwig, fine-tuning and training, and for Lorax. And there's just a lot of discussion going on, interesting examples, resources. We would love for you to come and join our community or email us to support@predibase.com at any time. Thank you very much. And I would be now happy to take some questions. So I just put a note into the chat to see if anybody sees that, if that's where the questions will be. We'll wait a minute to see. And I'm hoping I'm in the right chat session. I see. So, all right. Well, If there are no questions, oh, there's a question. Khalid Yunus, how is Predibase different from other companies who use fine-tuning like LR-Train? Khalid, I am sorry, I'm not familiar with LR-Train. Please join our Discord and go to the Predibase group and ask there. We'll be happy to find out. We know there's fine-tuning is done in a number of ways by different companies. This particular one, I don't know, but we'll be happy to, see you in our Discord, and we will get the answer for you. Okay, so that was the previous question. Looking for another question. Oh, that was from previous session. I see. That particular LR train was previous session. I was in this room, so I didn't see that session, but we'll go take a look since now in the chat recording, and we have team members from Predibase here, so this will not fall through the cracks. Thanks for your question, Khalid. Well, thank you all for attending. Please feel free to enjoy and experiment with the shared resources. Come join our community on Discord to ask any questions, try Predibase, and learn more about LLMs and fine-tuning. Thanks so much, everybody, for